A pleasant day to everyone. I am Sir Miko Eroles and welcome to this presentation on the Magma mixing genesis of the Mafic Enclaves and their associated granitoids in the Can-Granite Gneiss complex of Central Cote d'Ivoire. This study combines fieldwork, petrography, and geochemistry to show how interactions between mafic and felsic magmas shape the region's granitoids in the subduction-related setting. So to start, magma mixing occurs when two chemically distinct magmas mix to form a hybrid magma. Mafic microgranular enclaves, surreal minerals out of equilibrium in their host rocks, bedded rocks, and hybrid rocks are the main observations that attest to magma mixing. These characteristic features of the magma mixing are observed in the intermediate and felsic calc-alkaline granitoids. Mafic microgranular enclaves show preliminary evidence of mantle heterogeneity and the role of mafic magmas in the initiation and evolution of the calc-alkaline granitoid magmas. In this paper, the evidence of magmatic mixing that will be studied are the mafic microgranular enclaves, and these enclaves, which vary in size and shape, outcrop the granitoids of the Can complex. The aim for this study is to establish the field relationship, mineralogical composition, and geochemical interaction of the mafic microgranular enclaves with the Can granite gneiss complex. The Can granite gneiss complex is situated within the Manlio rise of the West African Craton. This craton is a complex mosaic of ancient terrains, and the Manlio rise itself is divided into two distinct domains by the Sassandra Shear Zone. The western Kenema-Man domain is dominated by the Archean rocks, Migmatites, gneisses, granulites, and charnokites, dating back 3.2 to 2.75 billion years. In contrast, the eastern part of the Manlio rise is characterized by the Paleoproterozoic rocks formed between 2.25 to 2.05 billion years ago. These include Tulitic and calc-alkaline volcanics, granitoids, and volcano-sedimentary sequences. This complex history provides a crucial backdrop for understanding the formation of the Can complex itself. Can granitoids were distinguished with three major groups composed of the Can River group, the volcanic group, and S-type intrusive granitoids. The Can complex consists of amphibolite facies TTG, myelinitic orthogneiss, mafic ultramafic rocks, and myelinitic gneiss. In recent works, the granitoids of the Can complex are interpreted to originate from the juvenile crustal growth within the Paleoproterozoic origin at the boundary of the convergent plane. Now, let's shift our focus to the key feature of the Can granitoids, the mafic microgranular enclaves or MMEs, as you can see in this image. These enclaves exhibit a remarkable diversity in the size and shape. They range from just a few centimeters to several decimeters in length. Notice the texture. These are the dark color rocks with the fine-grained microgranular appearance, as their name suggests. However, some enclaves present a fascinating detail. They contain phenocrysts of feldspar and amphibole. These minerals are characteristic of the surrounding host granitoids, strongly suggesting that these enclaves incorporated material from the host magma before their final emplacement. The distribution of these enclaves is also noteworthy. Sometimes they occur as isolated bodies, other times they are clustered together in groups, and their shapes also vary considerably. Many are subrounded or rounded, which is consistent with partial assimilation of the surrounding magma during their formation. Others are elongated, even spheroidal, indicating different flow dynamics within the magma. The most frequent shape, however, is ovoid. The sheer abundance of these enclaves is itself significant. It points to a high frequency of interaction between different magmas during the formation of the Can complex. Finally, observe the contacts between the enclaves. They are strikingly sharp with no evidence of significant deformation. This suggests that the enclaves were in place relatively rapidly and did not undergo significant interaction or mixing with the surrounding magma after intrusion. In this paper, the two analytical methods were conducted by looking through the mineral chemistry and geochemistry of the sample. For mineral chemistry, the chemical composition of the amphibole and biotite minerals in the mafic microgranular enclaves was determined using the Chemica SX100 microprobe at the Infirmary Laboratory in Brest, France. Biotite and amphibole standards are used in the analytical procedure for silicon, aluminum, iron, magnesium, titanium, chloride, and fluoride. To determine the state of the chemical composition, analyses were conducted on 8 fresh rocks, including 4 samples of mafic enclaves and 4 samples of host granitoids. The concentration of major oxide was determined using X-ray fluorescence spectrometry. Trace element concentrations were analyzed using the inductively coupled plasma mass spectrometry. The result of this study were divided into 3, namely the sample description, mineral chemistry, and geochemistry data. Let me start with the sample description. Microscopic observation revealed that the mafic enclave sampled from different localities exhibit nearly similar mineralogical assemblages. The mineralogy is composed of amphibole, biotite, plagioclase, quartz, and accessory minerals. In mineral chemistry, amphiboles are one of the main halogen minerals capable of recording magmatic events. Microprobe analysis of the amphiboles are given in the table 2. The amphiboles originate from the mafic microgranular enclaves in the samples, and they have intermediate contents of silicon oxide and low contents of titanium oxide and alkalis. The amphiboles were projected in the classification diagram, and the diagram shows that the mafic enclaves are composed of amphiboles with values flashed on the screen. Biotites can be also used to estimate the conditions of the genesis of the magmatic host rocks, and these results show high concentration of magnesium oxide, low concentration of aluminum oxide, and iron oxide. Magnesium to magnesium iron ratios indicate that there are magnesiobiotites. Analysis of this diagram shows that the biotites in the mafic magmatic enclaves were generated by calc-alkaline magmatism. Enclave biotites lie on the boundary between the realms of orogenic soothes and S-type magmas, as you can see in this figure 4. For geochemistry data, it is divided into 2, the major element and the trace element. For the major element, the chemical composition in silicon oxide vary from 53.5 weight% to 64.5 weight% for the mafic microgranular enclaves, with an average of 59.06 weight%. For the host granitoids, the silicon oxide composition ranges from 62.4 weight% to 70.8 weight% with an average of 68.08 weight%. These compositions are intermediate and intermediate to felsic respectively. According to this nomenclature, MMEs are composed of tonalite and monsodiorite. The most granitoids range from tonalites to granodiorites and granites. The silicon oxide versus alkaline ratio diagram shows that the microgranular mafic enclaves and their host granitoids have calc-alkaline affinities. In detail, these rocks belong to the medium potassium to high potassium calc-alkaline series according to this diagram. The relatively low A to C and K values ranging from 0.62 to 1 show that the MMEs and their host rocks are metaluminous. This metaluminous character and the absence of peraluminous minerals demonstrate that all the rocks studied are type 1 granitoids. For trace elements, the rare earth and multi-element patterns can be seen in figure 6. The rare earth elements show comparatively similar and most flat heavy rare earth profiles with an average dysprosium lutetium of 1.36 for the mafic enclaves and 1.27 for the host granitoids. In granitoids, rare earth patterns do not show negative anomalies. However, 2 samples of host granitoids show slightly positive europium anomalies. These positive anomalies suggest that the plagioclases did not fractionate during the magmatic differentiation and that they are present in the form of cumulates. Based on the results, the granitoids of the Can complex displayed abundant mafic microgranular enclaves, double enclaves, and plagioclase megacrest, all indicating significant magmatic mixing in their formation. Sharp boundaries between MMEs and their granitoid hosts, along with varied enclave shape and sizes, suggest differences in magma viscosity and distinct magma sources. The structure of MMEs reflect mixing between high temperature mafic and low temperature felsic magmas through injection processes. The geochemical data of the can-complex granitoids and their mafic microgranular enclaves suggest that both fractional crystallization and magma mixing played significant roles in their formation. Key observations include Harker diagrams show linear trends indicating fractional crystallization. Scatter in rubidium versus strontium and barium versus strontium diagrams indicates that partial melting, not just crystallization, influenced trace element distribution. Both MMEs and host granitoids are metaluminous. Type 1 granites derive from partial melting of mafic to intermediate crustal rocks. Binary plots reveal that MMEs and host granitoids align along parallel lines, not passing through the origin, supporting the presence of multiple magma sources, magma mixing, and partial melting processes. The tectonic signatures of the can complex suggest that its mafic microgranular enclaves and host granitoids formed in a subduction-related continental arc setting, with distinct source characteristics. Primitive mantle normalized patterns show negative niobium, tantalum, and titanium anomalies, typical of subduction zone magmas. Titanium per aluminum oxide versus zircon per aluminum oxide plots place both MMEs and granitoids within the continental arc field, near the boundary of the oceanic arcs, indicating convergence of oceanic and continental plates. The absence of europium anomalies in some host granitoids suggests they were derived from the melting of a hydrated subducted oceanic crust, interacting with the mantle wedge at moderate depth. In conclusion, this paper presents strong evidence of magma mixing in the can complex, primarily through the study of mafic microgranular enclaves using field, petrographic, and geochemical data. Field and petrographic evidence tells that MMEs of various shape and sizes, with sharp boundaries and host feldspar phenocrysts within the enclaves, point to physical mixing of magmas. Moreover, geochemical evidence shows MMEs and host granitoids share intermediate to acidic composition and similar alkaline, metaluminous type 1 granite characteristics indicating chemical interactions between mafic and felsic magmas. And lastly, petrogenesis explains that the granitoids and MMEs form through mixing of basic mantle-derived magma and felsic crustal magma within a subduction-related tectonic setting involving partial melting of the lithospheric mantle and continental crust. The study suggests further investigation via zircon-uranium lead dating to confirm whether MMEs and their host granitoids were in place simultaneously, supporting the magma mixing model. So that's all for the presentation. Thank you for watching.